Welcome to 3D. In this lecture we're going to look at a program called 3ds Max. 3ds Max is a 3D authoring package. It's used by artists to create mainly polygonal models and to render them. So I'm going to be showing you some code. You don't need to worry about learning the code, but it is extremely useful if you can pick up something about what the code does and understand how the code is working. So what we're going to explore is what the object transform is, how information is stored in a matrix. Then we're going to look at matrix multiplication and how it affects the vertex position of a mesh. We're going to look at what local space is and how to convert from local space to world space. We're going to look at how projection works and how the inverse of a matrix enables the projection. And then finally we're going to look at how perspective works. So to begin with, let's have a look at 3ds Max. So this is the objects transform, and you can see we have 3 columns and we have 4 rows. I've written a function to make this slightly easier to see. So if I just try PM object, you can see that it will print out the matrix in a more familiar way. So we can see here, definitely got 3 columns, definitely got 4 rows. So this is the object without scale or rotation, and it has the following transform. So we have a 1 0 0, a 0 1 0, and a 0 0 1, and then we have a bunch of zeros at the bottom. And we're dealing with 3D. So the question is, why have we got this extra 4th row? Well, if we just ignore this 4th row for the moment, we just look at these first 3. So we have a 3 by 3 matrix. This is the identity matrix. It is 1 in the world of matrices. So why the extra row? Are we not dealing with 3D? Well, we are dealing with 3D. Should the matrix not be 3D? Yeah, the matrix should be 3D. However, we can't encode all of the information of 3D in a 3D matrix in the same way as we were unable to encode all of the information about 2D in a 2D matrix. So when we looked at the 2D matrix, we could see that the scales Sx and Sy were encoded along the diagonals of the matrix, and in the 2D rotation we could see that the rotation formula again was encoded in the matrix with cosine A, minus sine A, sine A, cosine A. So we can see how we can encode both scale and rotation into a 2D matrix, but we couldn't encode position. There was nowhere for us to put that extra, so we needed a new dimension. We needed to add a 3rd row into our 2D matrix, and it's the same in a 3D matrix. In 3D, the 3 by 3 matrix cannot encode all of the 3D transform, so the matrix needs to be 3 by 4. And we can check this by looking at the actual model. If we move the object minus 20 in the x and minus 5 and 5 in the y, let's see what matrix we get. Let's move our teapot. Let's make this minus 20 in the x and 5 in the y. And let's bring back my listener. And let's find out what the transform matrix is. And you can see that the first 3 rows are the same, but now we have a minus 25 in the 3rd row, which corresponds to the position of the teapot. So we can see that the x and y positions in the matrix, and this is why we need the extra row. So okay, so we can understand where the position offset comes in terms of the matrix. let's have a look at our scale and rotations again. The teapot, let's scale our teapot up. Let's do a non-uniform scale. Let's put 200 and 300 and 500. So now we have a much bigger teapot and a rather distorted teapot. And again, if I have a look at the transform, you can see our 200%, because Max uses a percentage scheme, is twice as big. So it's 2 in the X, 3 in the Y, 5 in the Z. So you should be able to see how a matrix encodes position and scale. So it's like this. We have Sx, Sy and Sz, which are the diagonals of the matrix, which were previously 1 because it makes sense that everything should be scaled by 1. And then we have the offset Px, Py, Pz. Okay, so now let's go in and consider rotations. So if I go in and I rotate this object, and I'm just going to set this to minus 30 degrees. And again, let's have a look at the transform. And that looks pretty nasty. There's a lot of numbers in there. They don't mean a great deal of sense to me. We can see that the position hasn't been affected by the rotation, or we can see that the Z scale hasn't been affected by the rotation, but the first two rows have definitely changed into some arbitrary numbers. And so we would really like to know why these particular numbers, what have they got to do with the rotation. Well, one way to solve this problem is to try and fix the scale back down to uniform scale. Okay, so you can now see that these numbers still are very nasty, doesn't necessarily mean anything. We have a 0.866025 and then a minus 0.5 and a 0, and then we have a 0.5, 0.866025 again, and then another 0. And then the last two rows, again, it's as expected. 001, which is the scale, our Z scale is now 1, and our position of the object. So what do these numbers mean in these first two rows? Well, let's have a look at the cosine of 30. And we can see that the cosine of 30 is indeed 0.866025. And let's have a look at sine of 30. And again, we can see that sine of 30 is 0.5. So what this actually reads is this is the cosine of the angle, this is minus the sine of the angle, this is the sine of the angle, and this is the cosine of the angle. So this is definitely how our matrix is encoding the rotation. Cosine of the angle minus the sine of the angle, comma 0. Sine of the angle and then cosine of the angle. And this looks familiar. And in fact, this is our, if you just looked at these two, this would be our 2D rotation formula, because our 2D rotation is in the z-axis. Now you will also note that the rotation that I put in, if I go back to my rotation, is a minus 30. But I've asked for the cosine of 30. So the question is, why is this minus 30? And that is to do with the direction of the z-axis. When we were working in 2D, z was going into the screen, so positive was further away from the viewer and further into the screen. But in Max, z goes up, so it's going up here This is positive Z pointing up. That's positive Z. And the problem with it pointing up is it's actually pointing in the opposite direction. If we look down on this, you can see here that we have our x-axis and our y-axis, and our z is coming towards us. So it's in the opposite direction. And because z is in the opposite direction, the rotation is in the opposite direction. So we have to consider whether rotations go clockwise or anti-clockwise. We have to consider which direction the z-axis is in, and we have to consider which axis system, whether you're using a left-handed or right-handed system. So that may be a little confusing. The underlying maths is always the same. So that is the matrix, and that is how we encode information into the matrix. Every object in a 3D scene will have this matrix. It will have a transform matrix associated with it, which enables that object to move around the screen. It enables the object to rotate about, and of course it enables the object to scale. The next thing we're going to look at is we're going to have a look at scene, and we're going to see how to render those vertices of the objects. So here you can see that we have a three-dimensional scene with a teapot and a cube and a torus. And I've got some code here that basically does a dot render. In other words, what we're going to do is we're going to build ourselves a bitmap. Then we're going to go through every object in the list. Then we're going to go through every vertex of every object in the list. We're going to get the vertex position. And then we're basically going to scale it up so that we can see it. And we are going to plot the pixels on a background. And all this does is it plots 4 pixels instead of just plotting 1, so it's a bit easier to see. So if I run this, you can see that we get the classic problem of all of the vertices are up in this top left hand corner. Remember that this will be 0, 0. And we really want 0, 0 to be the center of our screen. Okay, so let's fix this. So what I'm going to do is I am just going to take our vertex position, and I'm just going to add half of the bitmap width and half of the bitmap height before I actually plot the pixel. And what that will do is it will shift it over into the middle of the screen. So there we have our teapot, but where is our box and where is our torus? So let's have a look and see if we can identify these. I'm just going to take this torus and I'm going to scale it up a little bit. Technically I'm not scaling, technically I'm changing the geometry. So let's be clear, not scaling it, I'm making it a bigger object. And if I come back over to here and I execute it, then you can see the torus has got bigger, but it's still centered around the origin. Despite the fact that we can clearly see that the torus is not on the origin. Again, we can clearly see that this box is not on the origin. And yet when we render, they appear on the origin. And this is because this is how vertices are stored. They're stored in local space. They are stored relative to the object, and it is the object that moves around in the world, not the vertices. So this is where the matrix transform comes in. What we have here is some code that will take, we're getting the vertex from the mesh, and we're going to get that vertex, and then we're going to multiply it by that object's transform, in other words the matrix. And now you can see that when I multiply the verts by the matrix, you can see that the objects are now in world space. Our teapot is still at the origin because it's at the origin in world space, but our chamfered box and our torus are both in the correct position in world space. Okay, that's good. Let's make sure that it works. Let's just give this a little bit of a scale, and let's rotate our teapot, and let's rotate the torus, and we don't need that anymore. I'll run it again, and now you can see there's our torus rotated, there's our chamfered box which has been scaled, and there's our teapot again which has been rotated. So let's just move them around a bit as well. Let's move this to the other end. Let's move this over here. Again, you can see that the torus and the chamfered box have moved. So the transform allows us to take vertices which are in local space and transform them into world space. And that's what the objects transform does. Okay, so at the moment we are looking down on these objects. And you may also have noticed that the relationship between what we're seeing when we look down on the objects and what we're rendering is flipped, because positive y goes up on this screen, but when we render, positive y goes down on this screen. So things are basically being inverted on the y-axis. Okay, I'm just going to reset the scale on this object. And I'm going to move it out of the way a little bit. Okay, so we're looking down on the z-axis. We can also look along the y-axis, and we can do this just by putting into the y-axis the z-axis, in which case I'm using the negative z-axis. Let's make sure we get things in the right order. Right, there we go. So now we're looking down the y-axis. So we're looking through this view here. And you can see that there's our torus, there's our teapot, and there's our box. So we can change axes. This is quite useful and is fine for flat gaming, but what we really want to do now that we're in 3D is we want to be able to look at this through the eyes of a player or through a camera. It's much more useful to be able to have an object in the scene and then look through the scene through the eyes of that object. And this is obviously going to act as like a camera or a player in our game. And the way that we do this is that when we convert from local to world space, we multiply by the matrix of the object. But when we want to convert from world space into local space of that object, we actually multiply by the inverse of the transform. So basically what we're doing by converting from world space into local space of this camera, we are converting it into a camera view. So let's go and put the code in for this, and you can see that basically what we have here, this is our transform of the camera. We take the inverse of that transform and we multiply it by the vertices. So if we do this and we evaluate it, you can see that we get a very similar view to looking down the y-axis. So let's just see if this is actually working. I'm going to lift it up in the Z. I'm going to calculate it again. You can see our objects have moved. I can move it over in the X. Again, our objects have moved. And what I can do, of course, is I can rotate this. So it's now looking down on the objects. And again, I will render this And you can now see that we are looking down on those objects. We're getting an orthographic view. That is, there's no perspective, but we can definitely see that this view is the view that the virtual camera is using. So this is our virtual camera, this is us looking down the camera. And again, if I rotate the camera around so that it's looking over here, and I give it another render, you can see again, this is what we get. So let me just straighten the camera out a little bit so that they are more similar. There we go. So we get a direct correlation between this projection and this projection. One of the things that we are definitely missing, however, is perspective. There's no foreshortening and there's no perspective. So we need to add some. So first of all, what I'm going to do is I'm going to add another teapot to show exactly what I mean. So we're going to have two teapots in the scene. And I'm going to add this teapot to my list. Hopefully that should do it. And if I evaluate this, you can now see that we have two teapots. Even though this teapot is further away than this one, it is the same size. And again, I'm just going to move it even further back. Let's make sure that it's in view. And render it again. So you can see these two teapots are the same size, so there is no perspective. So how can we synthesize or simulate the perspective into our projection? Well, we know that the further away an object is, the smaller it should be. We know that the center of the screen is the origin, and we can see by looking along this z-axis, you can see that the further away we get from the origin of this camera, the bigger Z is going to be. So Z will get bigger as we move further away from this virtual camera. So the Z value for this object will be bigger than the Z value for this object. So what we want to do is we want to divide by Z. So what I'm going to do is I'm going to put some code in that divides by Z. One of the key things about the division by Z though is normally it is too big a value and everything gets shrunk to a tiny little point. So what I'm going to do is I'm going to take the Z position and I'm going to multiply it by a small decimal to scale down the Z position, which will make it smaller. The Z position will be smaller, therefore the division will be less small. In other words, the division will shrink the X and Y values less. There goes my dog. Where were we? We were looking at this Z parameter, which basically makes sure that our Z is not too big. So we're basically shrinking the value of Z so that it has less impact on X and Y values. So the X value becomes smaller the further away it is from the camera 0, and the Y value becomes smaller the further away it is from the camera 0. And we are dividing X and Y by ZP. And ZP is just a scaled value of Z. So let's have a look at this. Nope. So what we can see now is we can see that this is the teapot that's close to the camera, and this is the teapot that's far away, and we can definitely see a scale difference. We can see that we have perspective. And what ZP is effectively doing is it's controlling that particular scale value, or the size of the lens that we're using. So if I change this to just a 0.1, still pressing the wrong button, you can see that we now have a much wider angle lens. And because the lens angle is much wider, we're getting more of the scene in, but the objects within the scene are going to get smaller. And that's because of the size of the lens. We can do the reverse. Let's make that 3. So now we have a telephoto lens. So in other words, you're zooming in to things that are off in the distance. Let's put this back. Let's just move this a little bit. So you can see now we have a virtual camera, and we can move this camera around the scene just as if it was an ordinary object, and we can see the scene through that camera. So this is how you can get a perspective projection. So what we have done is we've looked at objects, we've looked at their matrices, we've seen how the matrices take the vertices of an object and convert them from local space to world space. Then we've looked at how the inverse of an object's matrix can be used to convert from world space into view space, that is, the local space for a camera. And then what we've also looked at is how the Z coordinate can be used to generate a form of perspective, and how we can control the camera lens for that perspective.